Hi everyone, my name is Meera Singhal.
And I'm Foley.
And I'm Sanan.
I'm Shannon Callahan.
I'm Cablayan.
And my name is Lucy O'Brien.
We are the Grace follow-on team with the NASA SEAS internship. In our project, we utilize GRACE and GRACE follow-on data to track ice sheet and glacial melts in Greenland, West Antarctica, and East Antarctica, estimate these regions' contribution to sea level change, and project sea level change into the future. Launched in March of 2002, GRACE, or Gravity Recovery and Climate Experiment, was a satellite in collaboration with NASA and the German Space Agency. The GRACE mission is composed of two twin satellites, GRACE A and GRACE B, one following the other in a near circular polar orbit. GRACE has the ability to detect minuscule changes in Earth's gravitational field by tracking the inner satellite range with a precision of about 0.1 micrometers, equivalent to the distance change of about 1/10th the width of a human hair. GRACE was replaced with GRACE Follow-On, or GRACE FO, in 2018 with a nearly identical design. Our project utilizes GRACE and GRACE Follow-On's monthly gravity measurements, which are influenced by mass changes in water systems and geological events. Our primary objective was to use the GRACE Follow-On data to model ice mass loss in polar regions and the corresponding effects on sea level changes. This involved processing GRACE follow-on's range acceleration data using Python and converting the gravity anomalies to equivalent water height and eventually to ice mass change.
So, to begin modeling ice sheet loss, sea level change, and projecting these processes into the future, we obtained laser range acceleration, or LRA, and K-band range acceleration, or KRA, data from GRACE and GRACE follow-on. LRA and KRA data allow us to graph gravity anomalies from the follow-on mission, as seen in the figures featured on this slide. This specific data factors out static gravity anomalies, which is the picture on the left, leaving what is referred to as temporal gravity, the minute variations in Earth's gravity that change frequently, and with which GRACE and GRACE follow-on are able to detect. From the LRA and KRA data, one can derive the equivalent water heights of any geographical region of the Earth, as shown on the slide. Equivalent water height essentially describes the change in mass in terms of the water thickness of the melted ice covering the whole region we are looking at. To derive equivalent water height, the LRA and KRA data is converted to gravitational potential. After this conversion, geological phenomena are removed, such as post-glacial rebound and crustal uplifting. Events such as these frequently cause changes in local gravity levels, but are not pertinent to our objective of understanding Earth's changing water distribution. In other words, removing these disruptions allow us to focus more effectively on changes in Earth's hydrosphere alone, compiling the equivalent water heights to be used in the next steps of our project. This conversion from range acceleration residuals to equivalent water thickness is beyond the scope of our project, so we worked directly with the equivalent water thickness data.
We decided to visualize the equivalent water height data in a heat map animation in order to better understand its changes over time. As shown, there are clear trends of decreasing water height around Greenland and West Antarctica, while East Antarctica showed trends of increasing water height. This was our motivation for selecting these regions and conducting further analysis. To calculate each region's change in mass, we employed a global grid division approach, dividing the Earth into cells measuring 0.25 degrees latitude by 0.25 degrees longitude. We then focused on the desired regions of Greenland, West Antarctica, and East Antarctica by masking each region. The primary challenge in this approach was accounting for Earth's spherical geometry. Cross-sections of the Earth are not rectangles, but are rather sectors of a circle when visualized in 2D. Consequently, grid cell areas vary with latitude, since equatorial grid cells are larger than polar cells. To address this, we calculated each grid cell's area using equations 1, which can then be simplified to equation 2 to get the mass change for each cell by multiplying its equivalent water height with the grid's area and the density of water. The total mass change for each region was obtained by summing these individual cell contributions, which effectively accounts for the latitudinal variation in grid cell size. To convert mass change to sea level rise contribution, we divided the total mass change by the global ocean surface area. This gives us each region's specific contribution to sea level rise over the study period. When we did so, we uncovered a few interesting observations on each of our selected regions.
In two of the regions we looked at, Greenland and West Antarctica, there was a significant annual decrease in mass, primarily surrounding coastal regions, and a corresponding contribution to the increasing global sea level on a consistent basis. This is reflected in the figures displayed here, where we see that the annual rate of mass change for Greenland is a decrease of about 236 gigatons per year, and for West Antarctica, a decrease of about 106 gigatons per year. It is also represented here, where we see that the annual contribution by Greenland to global sea level is about 0.64 millimeters per year and roughly 0.28 millimeters per year for West Antarctica. Notably, Greenland appears to contribute the most on a global change in sea level, and regardless of size, has lost the most mass over the period studied. There are a number of potential reasons for which we see this trend emerge. Among them, and most likely, are rising temperatures and ice calving. With regards to rising temperatures, a factor notoriously associated with climate change, this causes ice sheets and glaciers to melt, forming melt ponds that further increase melting speed, or in other words, create a feedback loop. From here, water seeps into the surrounding ice sheets, lubricating their bases and accelerating their movement into the ocean. The second mentioned region for which Greenland and West Antarctica may be experiencing the changes that they are is ice calving, or ice mass loss. This occurs when icebergs break off from glaciers and flow into the ocean. This process is influenced by ice flow velocity, thickness, and ice shelf area. Of course, without a deeper analysis of these regions, we can only postulate as to which specific processes have caused the changes we have observed. This is true as well for East Antarctica, the third and final region we would like to discuss.
East Antarctica served somewhat as a surprise for our team. Contrary to what one might expect, we observed in East Antarctica that there was a net positive rate of mass change and a net negative contribution to global sea level. With regards to this pattern, it is important to recognize scale. For instance, the magnitude of the mass change and sea level rise in Greenland are nearly 700% greater, respectively, than those of East Antarctica. What's more, the size of the area covered by East Antarctica is considerably larger than that of either other region studied. Regardless, however, this pattern is notable, and as is the case for Greenland and West Antarctica, there is a reason for which such an anomaly may be presenting itself. Specifically, a consistent increase in the magnitude of precipitation received by the region due to global warming and changing atmospheric conditions may be coming into play. It is this complexity that led us to the final step in the research process, analyzing the extent to which these regional changes impact the Earth as a whole. For context, however, the image featured here depicts the size of a single gigaton of water relative to New York City.
The Earth is a delicate chemical, physical, and biological system. It possesses mountains, glaciers, a fluid core, and more. All of these complex features ultimately lead us to one important consideration. No change in Earth's function or resource distribution will be felt equally in all parts of the world. As we look over GRACE data and analyze the effects of climate change in global sea level change, it's important to note that said effects are not felt with uniformity across the world. This is due to several processes and anomalies such as crust deformation and shifts, as well as Earth's rotational axis. Because sea level rise is not distributed equally across the globe, we have to scale each region's contribution to sea rise. Here we can see a gradient fingerprint map for each region we studied, illustrating the consequent changes in water height as these regions discharge the mass in the form of ice and water. These maps depict the distribution of 1 millimeter of ice sheet melt from each respective region, distributed around the globe. As you can see by the hotter colors, equatorial and Pacific regions are disproportionately affected by sea level rise as compared to more polar regions. The animation on this slide shows sea level change projections based on current data collected from GRACE and GRACE follow-on. At the current projection, the sea level is estimated to rise by 75 to 100 millimeters, nearly around the globe by 2100. It is important to note that these are only estimated contributions from Antarctica and Greenland and is not the whole picture. Other factors such as temperature, thermal expansion, and more also play significant roles in sea level change.
To conclude, West Antarctica and Greenland are experiencing large-scale mass loss of -236 and -106 gigatons per year. Even though a majority of our climate is losing ice mass, East Antarctica is experiencing a period of mass gain at approximately 35 gigatons per year. West Antarctica and Greenland are contributing to global sea level rise at rates of 0.64 and 0.28 millimeters per year, with Greenland contributing the most. Overall, global sea level decrease in polar regions and rises around equatorial regions are likely due to variations in gravity, crust deformations, and shifts in the Earth's rotational axes, contributing to the unequal distribution of sea level changes.
With these results presented, our team would like to take a moment to speak about our experiences with the SEAS program this year. Here, we include a few highlights and challenges of the internship on the whole for anyone interested in reading, but at this time, we would like to each share our own perspectives. To begin, I would just like to say that these past 14 days have offered me some of the most enriching research opportunities of my high school career and have exposed me to so many different and exciting perspectives and people that I would otherwise never have had the opportunity to explore. Thank you, and I will now pass the mic off to my fellow team member, Om.
Overall, these 2 weeks in SEAS have been great. Not only have they been an opportunity to work on our project, but they've also been an amazing learning experience. I've had the chance to collaborate with gifted students from around the US, meet renowned NASA employees, and also partake in other projects such as microgravity Z-cube research, which are all helpful to my future STEM career. I'll now open the mic for anyone else who wants to pitch in.
The past 2 weeks as a NASA SEAS intern have been filled with so many opportunities that have given me amazing new insights into sides of STEM that I am less familiar with. I've always been interested in astronomy and astrophysics, and this passion remains. But through the GRACE project, I have been provided with a new perspective on global issues, which I strive to keep in account in my future studies. There were some challenges, mostly technical, such as getting rained on with the Z-cubes and navigating confusing data collection methods. I also learned so much about coding and data analysis with the help of my amazing teammates and mentors, which I will definitely be using in my future education and careers. The time flew by so quickly, and I'm going to miss everyone here, but it was an amazing experience, and I'm so grateful to have had it.
Overall, I would say the SEAS program has reaffirmed my career ambitions. I still want to go into the STEM field, but with a differing path, specifically in combination with public policy. Focusing on addressing disparities associated with STEM education and ensuring the perpetuation of funding for vital agencies such as NASA and the Department of Education. This internship has given me so much insight into the absolute necessity of keeping funding for programs like this available. As I continue my path in public service, I plan to pursue both a political science and a degree in electrical engineering to gain both a technical and civic understanding in policies regarding STEM education/tech policy.
So like my teammates mentioned, SEAS was just such an incredible experience to meet students from around the country who are interested in learning about Earth and space science, math and physics, coding, and other really nerdy topics. SEAS has prompted me to really consider collaborative STEM research as a career choice because of the exposure that I've had working with so many dedicated and passionate students and mentors.
These past 2 weeks have felt like a fever dream to me. When I first heard that I was accepted into this program, I fully thought it was a prank, and 3 months later, I still do. Before coming into this program, I wanted to complete my associates, get a degree in economics, and maybe minor in environmental sciences. But now I want to pursue a degree in environmental engineering. Our mentors, Chirag and Chaoyang, were instrumental in every step of this process, from patiently explaining matrices and simple geometry to helping us troubleshoot our code. I could not thank my teammates and mentors enough for making this experience the way it was. Thank you all for a life-changing 2 weeks. Before we end, though, there are so many people that we'd like to acknowledge in helping make our project successful. Firstly, our mentors, Chirag and Chaoyang, then the NASA Seas staff, especially Margaret and Selena Miller, then the UT Austin Center for Space Research for letting us use their facilities every single day, University of Texas at Austin for letting us sleep and eat there, and all the guest speakers and staff for their amazing presentations. Thank you all so much for listening. And if you have any questions, please raise your hands now.